Hi, Luke McKinney, Prep 101's Civ 100 instructor. We'll be looking at distributed loads in this video, how to replace them with point forces at certain locations. These can turn up in frames and machines, and they're also a key part of any shear and bending moment diagram problem.
A distributed load is a load that's distributed. Okay, video over. No, there's a bit more to it than that. Up until now, we've been looking at point loads. We have problems like if we have a beam with a pin at A and a roller like B, and we just have a single point force of 20 newtons down, like there was a mass pushing down there, or there was a beam pushing down at that point. And we'd label that point C just to make it easier for ourselves to deal with. But we're not always going to have single point loads like that. You might have a distributed load. Like let's say you had a bridge with a lot of cars constantly flowing over it, or you had a bridge or embankment holding up a load of mud or a load of water. Fluid problems have a lot of this distributed load stuff. So instead, you would have a situation with a pin at A, a roller at B, midpoint C, and instead of having single point loads, you could have distributed loads. Like you might have a constant load of 10 newtons per meter acting all over the beam there, and a load increasing from 0 to 10 between those 2 points, and then be asked, find the support reactions, which would be at A and B. Sometimes that's the whole problem. Sometimes that's something you need to do at the start to move into the rest of the problem. So how would we do that? Well, first we have to work out how to deal with these distributed loads. And what we do is we replace them with equivalent forces at certain locations. The first kind is a rectangular or a constant load. Now we can see if we have a constant load over a length, then the equivalent force is just the distributed load times the length. For example, if this was a load of 10 newtons per meter over 6 meters, then we've 10 newtons for every meter times 6 meters gives us 60 newtons. Makes sense? And we can see another cute thing about this. This is the distributed load, the height there, times the length. So this is actually the area of the distributed load. And that works perfectly. It's not a one-time coincidence. That's exactly what's going on there. So we can always use that as an idea. So where do we put this force? Well, this is at the midpoint of the distributed load. It's actually at the centroid of the shape. And the centroid of the load, the center of the shape, is at its middle. So we now have this equivalent force acting at the midpoint, half the length from the edges. The next type of load is the triangular load, which I'd sometimes call just increasing from 0. So we can see here, we've got a load increasing from 0 to some maximum value, and we want to find the equivalent force. Well, again, the equivalent force is just the area of this, which is the area of a triangle. So that's a half the height times the base. And that's applied again at the centroid of a triangle, which is a third of the distance from the maximum, or 2/3 of the distance from the 0 end. So we have that, a third of the distance from the maximum, or 2/3 of the distance from the 0. Why do I specify both? Because one will always tell you the other. Well, when you're doing these problems, your pivot point might be at either end, or it might just be more convenient to know one or the other distance. So it's always nice to have the tools ready to hand. The third and final type is the trapezoidal load, because it's a trapezoid shape, or I just sometimes call that the increasing load. It's not increasing from 0, it's increasing from one load to a second load. So how do we deal with that? Well, there's two ways of dealing with this. Whichever you prefer, it's good to know both of them. As an engineer, sometimes you have multiple options. It's tempting just to pick one and that's your best one, but you're better off just having all the tools available because you never know when one or the other might be easier to work with. The first is we divide it into two shapes. So we have a rectangle, and we know how to find the equivalent force for a rectangle. It's the distributed load times the length acting at the midpoint. So we replace it with our first equivalent force at the midpoint of the beam. And again, notice how I'm always saying the words. If I'm just saying that's F1 at L/2, that just sounds like I'm headbutting a typewriter. It doesn't actually bring the concepts across. Then the other shape is just this triangle, which has a height of the difference between the two distributed loads. So the second equivalent force is a half the height by the length, and that's applied a third of the distance from the maximum, the bigger distributed load. And you can see that comes quite nicely down to just two equivalent forces, and that works perfectly well. It's not the only way to do it though. It turns out trapezoids have existed for a while, so people have come up with a way of dealing with it. And if you prefer, you can just do the whole trapezoid in one step, which is the equivalent force is the area of the trapezoid, which is a half distributed load 1 plus distributed load 2. You'll see that's actually the average of the distributed load times the length. And that's located at a distance a third of the length, distributed load 1 plus twice distributed load 2 over distributed load 1 plus 2 from the distributed load 1 end. And if you're doing it that way, you get to replace it all with just one force that distance away. Now, if you have your choice, use whichever you like. I tend to prefer the rectangle and triangle because I'm just using the tools I used before more often, which means I'm better at them all the time. But some people like the neatness of the second formula, so I wanted to provide both of those for you. So let's put these into practice. Remember, if you haven't done an example, you haven't done the engineering. We want to find the support reactions at A and B. So the first thing we do in any problem like this is to break down the distributed loads into equivalent forces, because those we can work with. Let's look first at this triangular load. We can see the equivalent force is a half the distributed load times the length, which is a half of 10 times 6, which is 30 newtons. And that's at a third of the distance from the max, or 2/3 of the distance from 0. We can see 0 is at A, which is nice and handy, so that's 2/3 of 6 is 4 meters to the right of A. I always specify the location like that when I'm working it out, because I'm going to have to go back and draw the diagram in a minute, and I'd hate to have to do it again because I wasn't clear. Then we look at the rectangular constant load. So we have the equivalent force is the distributed load times the length. 10 newtons per meter for 6 meters is 60 newtons, and that's at the midpoint. So that's 6/2, 3 meters to the left of B, or to the right of C, whichever you prefer. So we draw our diagram now. We have A and B. We plug in the forces we found. We have 30 newtons down, 4 meters to the right of A. We have 60 newtons down, 3 meters to the left of B, which makes it 9 meters to the right of A. And then we have the support reactions. A is a pin, so it has a vertical and horizontal unknown component. B is just a roller, so it has our friend the vertical unknown. And then we're on to our standard procedure. Plug in our axes. We don't want to make a mistake with directions, so we always remind ourselves which way is plus. Always start with the moments. The sum of all the moments around some pivot is 0. We choose the pivot point with the most unknowns, which is A. B would actually work in this case, but we always practice our rules. So let's go through the forces now. The forces at A, the X and Y components, are pushing directly on the pivot. So they provide no moment. Just like pushing on the hinge of a door won't turn the door. Then 30 newtons acting down, 4 meters perpendicular, and that would turn clockwise around A, which is negative. Then we have 60 newtons down, 9 meters perpendicularly away, that would be turning clockwise around A, so that's negative. And finally, BY, the full 12 meters away, because that's the length of AB. Always complete our little diagrams. And that is turning counterclockwise around A, so that is positive, equals 0. One equation, one unknown. So we find BY is 55 newtons. That's positive, so it's in the direction we drew up. Then we move on. The sum of all the horizontal forces is 0. So the horizontal reaction at A is 0 newtons. Never skip that step. Even if something is 0, you got to show it's 0. And then the sum of all the vertical forces is 0. So plus AY up, minus 30 down, minus 60 down, plus BY up is 0. Well, we know BY, that's AY minus 30 minus 60 plus 55 is 0. So AY is 35 newtons. That's positive, so it's in the direction of the arrow we drew, which is up. And that's the support reactions for that beam. And you can do that for any distributed load question. You reduce all the equivalent forces to the out of the distributed loads, and you can solve just like a force problem. Just remember, if later on in the problem, if you cut it apart or you break the distributed loads into pieces, like if you've chopped the beam halfway, then you have to do the equivalent forces step again. You just can't assume that everything's the same as before.
I hope that was useful. There's plenty more videos in the playlist, but what's even more useful is lots of exam examples and exam specific advice. And that's what we do in the prep sessions. So join the Prep 101 Study Hub Facebook page to find out when those go on, and many of them are even free, so you definitely don't want to miss those. Hope to see you there.